Reduction. There are three reducing agents that we're introducing. First is your anhydrous lithium aluminium hydride. And note that it has to be anhydrous because the adding of water will cause the lithium aluminium hydride to break down. We'll show you the equations later. Next reducing agent is your aqueous sodium tetrahydroborate, or NaBH4. That one you can have it in aqueous state because the presence of water does not cause the breakdown of your BH4-. The final one is your hydrogen gas, which is a commonly known reducing agent. So in the reduction of aldehyde and ketone, the reaction is somewhat reversed relative to the oxidation of alcohol, because in this case now, the hydrogen is being added back. 2 hydrogen is being added back. And the hydrogen is added back where one will go direct to the C, the other hydrogen will be added to the oxygen. So therefore, in the case of aldehyde, you will produce 1 degree alcohol. In the case of ketone, you will produce 2 degree alcohol. Finally, it's also important to highlight the mechanism. In the reaction mechanism of lithium aluminium hydride and NHBA4, both of them will in fact release H-. The H- ions will then undertake a nucleophilic addition as illustrated in the mechanism here. And thereafter, for each of the steps, water need to be added because water will then provide the proton to the species here, which act as a base in order to produce your alcohol. However, in the case of hydrogen gas, it's just a reduction reaction. It involves actually radicals, and the mechanism is not nucleophilic addition. Let's take a look at this example here. If you were to add anhydrous lithium aluminium hydride, the only reaction that will happen is that the aldehyde would actually becomes alcohol. That will be the product that you get. The C to C double bond will not be involved in the reaction with lithium aluminium hydride because the H- produced is a nucleophile, and the alkene or C to C double bond will only chemically react with an electrophile. Let us now see what happens when we decide to use NaBH4. If we decide to use aqueous NaBH4, the product will still be the same. Aldehyde will convert to an alcohol. And again, the same thing is that the alkene will not react with the H- from your NaBH4 since H- is a nucleophile. Finally, we'll now take a look at an example if hydrogen gas is being used. If hydrogen gas is being used, then what you have is that you will continue to see aldehyde being reduced to produce your primary alcohol. And the key difference will be that the alkene will chemically react with the hydrogen gas to produce alkane. So therefore, one need to bear in mind, hydrogen gas is the only reducing agent that can react with aldehyde ketone, and it can also reduce alkene functional group. Let's now take a look at the chemical structures of lithium aluminium hydride and NHBH4. Both these are the structures, they are both ionic, and AlH4- is a complex anion. But more importantly, in the presence of water, water could actually attack the aluminium, forcing the AlH4- to chemically alter itself. And you can see that in the presence of water, lithium aluminium hydride in the presence of water will form lithium hydroxide, aluminium hydroxide, and your hydrogen gas. However, water is not able to actually interact with boron, given the fact that boron is a period 2 element and maximum can only have 4 outermost orbitals, and it does not have any empty d subshell to be able to accept the electron from water molecules. So BH4- is stable and does not chemically react with water. Finally, why is lithium aluminium hydride a stronger reducing agent than your NaBH4? You will learn later in carboxylic acid, the chapter, that only lithium aluminium hydride is able to reduce carboxylic acid to primary alcohol. Both NaBH4 and H2 are deemed to be too weak as a reducing agent to do that. So the reason why lithium aluminium hydride is a stronger reducing agent than NaBH4 is because we can now compare the size of the atom. Aluminium being the larger atom means that the bond energy between H to Al is weaker, and since it's a weaker bond, it is easier for the hydrogen to break away from aluminium and to be released as a H-. Second of all is that aluminium has a lower electronegativity than your bromine. Given the fact it has a lower electronegativity, it means that the difference in electronegativity between hydrogen and aluminium will be higher, meaning to say that there will be a larger dipole moment, and therefore it's easier for H to break away from aluminium and to form H-.